On this adventure, we're going to introduce internal direct products and look at several examples. Alright, so the definition of internal direct product is the following. Given two subgroups H and K of a larger group G, we define their pointwise product to be the set of all elements HK, where H is an element in H and K is an element in K. So how I think about this, and the right way to think about this, is that these are all elements in G that have the property that there exists a factorization of G where the first factor lies in the first subgroup and the second factor lies in the second subgroup. For instance, if you're talking about integers, let's ignore group theory. You could be talking about factoring integers into even numbers times multiples times threes, or multiples of 3 or something like that. Then this would be the type of set. That would be the multiples of 6 if I remember correctly. So that's what kind of set we're dealing with here. So with this definition in mind, the internal direct product, G is called an internal direct product of two of its subgroups if it satisfies the following three conditions. First, this set equation is true, which translates into this statement. Every element in your group can be factored as a product of an element, as a product of elements in each of the two subgroups. 2, the two subgroups have no elements in common except for the identity element, which has to be in both subsets because they are subgroups. And 3, for every element in H and every element in K, you have commutativity. H times K is equal to K times H. That doesn't mean that H is abelian or K is abelian, only that when you multiply an element in H times an element in K, this happens. Note the importance of this criterion is that it actually tells you that H times K is equal to K times H. And not only that these sets are equal, but that quite literally the bijection would be given by sending HK to KH because they're actually the same element. So it'd be the identity function. You'll see when I do the proofs, I only ever show that G is a subset of H times K because the reverse inclusion is already given. This part is always true by definition. Likewise, the fact that the identity subset, that one's also always true because the identity element is always in any element of every subgroup. And so it's always going to be an element in any intersection of subgroups. So even though this condition involves a bunch of equalities of sets, we're only ever going to be showing some of the inclusions. Here's our first example. Let's take the cyclic group, C mod AB. Notice that the element A bar has order B. A plus A is 2A. A plus A plus A is 3A, dot, dot, dot. When you add A to itself B times, you get AB. And AB is 0 mod AB. So A has order B. Likewise, the element B, by the same logic, has order A. In a group N, if integers modulo n, if you take any divisor D of n, the element D has order n over D. In particular, the cyclic subgroup generated by B has order A, and the cyclic subgroup generated by A has order B. I claim that Z mod AB is actually the internal direct product of these two subgroups. Well, let's check the intersection condition. Oh, and here I should point out the assumption we're making. A and B are relatively prime. So let's look at this intersection. So this would be something that's an element in here, would be something that's a multiple of both A and B. So that means it'd have to be R times A bar, R S times B bar. But if A and B are relatively prime, that's not actually possible. Anything that would be the only thing that would be a multiple of both of them has to be a multiple of their least common multiple, and if A and B are relatively prime, their least common multiple is their product, which means X is actually AB itself. So this intersection is trivial. So that's one of the three conditions for being an internal direct product. The third condition was this commutativity condition. Here there's really nothing to check because chi itself is abelian. So congratulations, this equality is true. By virtue of, it doesn't matter that you're talking about subgroups. So the only thing we need to check left is the first condition, that every element in this group can be written as a product. And so what does this product look like? Well, remember, HK is the set of things that can be factored as an element in H times an element in K. An element in H, we just discussed, looks like a multiple of A bar. Element in K looks like a multiple of B bar. And the group operation is addition, so we're looking at integer linear combinations of A bar and B bar. That is what this set is. And so our claim is that this actually gives you all the integers modulo AB. So the question you have to ask yourself, is it possible to get 1 as an integer linear combination of A and B? Well, yes, when they're relatively prime, this is the theorem of Bezout. So that means that at least the integer 1 is in this product of subgroups for H equal to this subgroup and K equal to this cyclic subgroup. Of course, that solves the problem because now if you take any integer m, you can just multiply through by these coefficients. MRA plus MSB is now also in the set, and so congratulations. If I just use bar notation instead and work modulo AB, I now actually have this equality. So every element in the integers modulo AB can be written as an integer multiple of A bar plus an integer multiple of B bar. So every such element is in this product set. And so integers modulo AB is in fact the internal direct product of these two cyclic subgroups. It's a slightly harder example, so something non-abelian. Let's consider a dihedral group, so symmetry group of a polygon on an even number of vertices, but once you divide by 2, you get an odd number. So we're talking 6 vertices, 10 vertices, 14 vertices, but not 8, and not 12. Let K be the cyclic subgroup generated by R to the n. So it consists of just E and R to the n. For the purposes of the proof, we have to emphasize n is an odd number. And let H be the smallest subgroup containing S and R squared. you can check that that would be this set of products, s to the j, where j is equal to either 0 or 1, times r to the 2I, so even powers of r. And you can check that the product of any two things of this form is also of this form. This is abstractly isomorphic to the dihedral group on n symbols, by the way, but we're not going to need that for this argument. So our claim is that G is the internal direct product of these two subgroups. So our three conditions to check. First, G is actually equal to this product set. In other words, every element in the dihedral group can be factored as a product of this form, where you have an even power of the rotation operation times the 180-degree rotation, or the identity. It's worth pointing out, this is the 180-degree rotation. Well, let's take an element in G. Then it must be the form s to the j, r to the I for some I and j. So if s to the j is 0, you have a rotation, otherwise you have a reflection. If I is even, then there's nothing to do. Just tack on a product with the identity element, which is an element in K, and x is already in H. It's already an even power of the rotation. So you're already in this product set. So the only interest is when I is odd. Either you have an odd degree rotation, or you have a reflection where the power of r is odd. Well, a sneaky trick is to cleverly multiply and divide by the nth power of r. So 180-degree rotation. And then since n is odd, odd minus odd is even. So this is an even power. So s to the j times r to the I minus n is an element in H. And r to the n, by definition, is an element in K. And so we've managed to factor x as an element in H times an element in K. So we've seen every element in G is an element in this product set. Second step, you have to show that the intersection of these two subgroups is the identity. That's not too hard to see because take any element in K, either it's the identity or it's r to the n. R to the n is an odd power, and it's a rotation. The only rotations appearing in the subgroup H have even power. So you're not going to get an even power to be equal to an odd power in this dihedral group because it's order 2n. It's worth pointing out there are examples where that can happen when you're working with the symmetry group on an odd number of vertices, but that doesn't happen here. So this is satisfied. It's worth pointing out that's the case. Yeah, these two assumptions are necessary if you work with an odd number of vertices or a number of vertices that's a multiple of 4. This step of the proof breaks down. Finally, look at this third condition. For all h and h and all k and k, we have this product, commutativity. Here there's actually something to show because the dihedral group is not abelian. But K only has 2 elements in it, so we can check directly what happens. Multiplying by the identity doesn't do much, so that's easy. Multiplying the nth fold power by a rotation operation from H. Ooh, I should have put the 2i here. Doesn't do much. Similarly, if I multiply a reflection by this 180-degree rotation, well then by the way the group operation works, I can move the rotation operation past s by negating the exponent. But this just replaces clockwise with counterclockwise, and a counterclockwise 180-degree rotation is considered the same as clockwise 180-degree rotation. So these are still the same elements, and look, it's commutativity again. So this condition is satisfied. So our claim is true. G is the internal direct product of H and K.